Welcome to the tutorial, Analysis Tools for Turbo Components. This video will show you how to analyze existing turbo machine geometries and components in CAESES. CAESES provides accurate and fast analyzing tools that help you to transfer imported turbo machinery geometries into parametric models for further optimization processes or extract their design properties. For that, we are going to show how to apply different analyzing tools to extract a centrifugal compressor's meridional contours, the blade's camber surface, and the blade angle distributions. Let's start by importing the geometry into CAESES. First, let's save the new project by clicking Save As in the main menu. Let's stay in the main menu and navigate to the section Import inside the top blue ribbon. Here, we choose the correct file type and select the geometry you want to analyze. Let's start to analyze the geometry by navigating to the Model workspace. At first, we can choose to rename the imported geometry if it makes the project easier to follow. In the first part, we are going to analyze the compressor by extracting its meridional contours. Let's change the view to Blade View, which is the conventional meridional plane in CAESES. Note that turbo features might not work properly or lead to wrong results if the meridional contours are defined in a different plane. Note that, to apply analysis features for turbo machine objects in CAESES, the imported geometry must be positioned correctly. Conventionally, the compressor is positioned in the negative z-plane with the trailing edge starting point at z equal to 0. If the imported geometry is positioned differently, you first need to translate and rotate it to the correct location. Otherwise, analysis features might return errors or lead to wrong results. Now, let's move to the Turbo section via the top blue ribbon and click on More to unfold further analysis tools in the Analysis section. Here, we select the feature, Transform to Meridional Plane. With this feature, we can transform 3D curves to the meridional plane, providing an intuitive and fast way of creating meridional contours from imported geometries. Let's start with the hub contour. To reference the correct curve from the imported geometry, activate the Curve Input window and click on the correct edge curve in the 3D View window while holding the Alt key. In CAESES, all objects that describe turbo machinery components should run along the direction of flow. Subsequent turbo analysis tools might not work properly or lead to wrong results if this convention is neglected. In this case, the extracted curve is running against the direction of flow, meaning we need to reverse the curve. To change a curve's direction, we can create an image curve and use the operation reverse. Another convention for turbo machinery features in CAESES is that the rotating axis is normally considered to be the z-axis and the direction of flow is along the positive z direction. Let's continue by applying the same workflow to extract the shroud contour from the imported geometry. Since the curve runs along the opposite direction of the conventional flow direction, we have to reverse it again. A quick way of reversing a curve in CAESES is to switch its domain interval. Now we can do the same procedure to extract the leading edge and trailing edge contour. Note that in CAESES the conventional direction for meridional contours such as leading edge or trailing edge is from hub to shroud. Again, it might cause subsequent analysis features to return errors if this convention is neglected. Since the blade fillet at hub prevents the edge contour to run all the way towards the hub contour, we need to extend the extracted leading edge. For that, we create an image curve and use the operation extension. Afterwards, we can use the operation trimmed by curve to trim the curve precisely at the hub contour. Let's reference the hub contour as the trimming curve. Now we need to switch to the meridional plane and select the correct curve to keep. Now, let's apply the same workflow to extract the trailing edge contour. Subsequently, we are going to extract the blade's camber surface. Let's navigate again to the turbo section via the top blue ribbon and unfold More to unveil the feature Extract Mean Camber Surface. First, let's reference the hub and shroud contour inside the feature. Then, we need to reference the faces from the pressure and suction side. Due to the filleted hub, the blade's pressure and suction side are not running entirely towards the hub contour. Since the feature's condition is that the sides of the blade must at least run towards the hub contour, directly referencing the faces could lead to errors. To extend the faces, we can create image surfaces from each side of the blade and extend them towards the correct direction. If possible, try to reference the faces from the blade that starts at the meridional contour plane. Similar to the extension of curves, we can use the operation extension to extend a surface. To extend surfaces into the correct direction, we can make the u and v domain vectors visible. Now, we can extend the surface at the start of the v-domain surface vector. After extending the pressure and suction side surfaces, we can reference them inside the feature. As a result, the feature is extracting the camber surface as a lofted surface between a defined number of section curves between the hub and shroud contour. Let's create an image surface from the extracted camber surface to check for the correct conventional turbo machine directions. Since the u vector is running along the opposite direction of flow, we need to reverse its domain interval. In the last part, we are going to extract the blade's angle distribution curves by applying two different methods. The first method extracts the angle distribution curves by analyzing the camber line curves, which can be extracted from the camber surface. To extract a camber line from the camber surface, we can use the curve type isoparameter, which returns a curve along a constant u or v surface vector at a given position. Now, we can reference the camber surface as input surface and adjust the positional parameter. Since we want to extract the camber line at hub, we can set the parameter to 0 and toggle the button, Switch UV Domain. Alternatively, we can extract a certain camber line from the curve list inside the camber surface feature. To do that, let's first create an image curve. Then, we can click the plus symbol next to the camber surface feature to unfold all objects inside it. By holding the Alt key while selecting the list, Camber Lines, we can reference the list in the source window. To access an item inside a list, we can write the command .at behind the list. Now, inside the parenthesis, to access the shroud camber line, we can reference the list again and write the command .getCount. This command returns the number of objects inside the list. Since the first object's index is defined by a 0, we need to subtract the number of objects inside the list by 1. Again, let's switch the domain interval to reverse the curve. For a better view on the angle distribution curves, we can open the 3D overview window. Simply right-click on the gray navigation bar on the left and click on 3D Overview. Since the camber lines have been extracted, we can navigate to the Turbo section and use the Analysis feature, Turbo Section Analysis. Let's reference the camber line and toggle the angle distribution curves you would like to extract from the imported geometry. By toggling the button, Beta 0 on Meridian, we can choose if the beta angle is measured from the meridional plane. Further, let's navigate to Visualization to create a 2D diagram for a better understanding of the angle distribution curves. Let's apply the same workflow to extract the angle distributions at shroud. As a result, we extracted the theta angle versus m' distribution curve in blue and the beta angle versus m' distribution curve in green in this example. Of course, you can also choose different angle distribution curves by toggling the buttons under the visualization settings. Lastly, in the second method, we directly extract the angle distribution curves from the blade or camber surface. For this method, let's use the feature, Turbo Blade Analysis. Here, we first need to reference the meridional contours we extracted in the first part, and then we are going to reference the camber surface. Note that if you want to reference a blade face directly, check for the correct U and V domain surface vector directions. Also, we can show different distribution curves at different blade heights at the same time by defining a list as the span position parameter. Again, to extract further analysis curves, we can simply adjust the visualization settings. Thank you for following along, your CAESES support team.